Okay, so today we're going to switch gears. Last time we did renormalization group, real space renormalization group. We discussed the pros and cons of it. There are many, many ways to do renormalization group transformations, and I'm going to show you in the homework, you're going to walk through another way to do it using a method called the transfer matrix. In one of the earlier homeworks, homework 2, you looked at the one-dimensional Ising model, and I showed you a trick where you take the 1D Ising model, then you add an extra spin to it, and then you worked out what the partition function for the system with n spins is for n+1 spins, when you know it for n, and then you devised a recursion relation and solved it, and then you use that to compute correlation functions. So that method, that sort of recursive way of doing it, can be generalized. And in my book, there are multiple versions of that trick described in one of the chapters. But the most general one is a method called transfer matrices. And that's what I'm going to teach you today. And this method is a very good one. It's used for numerical calculations. It is used for renormalization group calculations. It was the formalism that Onzaga used to find the exact solution of the 2D Ising model. And if you look at a famous book by Rodney Baxter called Exactly Solved Models of Statistical Mechanics, that is a book that goes through all the different ways that you can solve problems in statistical mechanics exactly. Interacting systems, but you can solve them exactly. And Baxter himself did many of these solutions, and they all come from various generalizations of the transfer matrix. It also is a way of going from statistical mechanics to quantum mechanics and quantum field theory. And so the way that in fact, if you go to a quantum field theory class, one of the things that they will tell you is the Feynman path integral is not well defined. So what we do is we do a Wick rotation, go into imaginary time, then the factor of e to the I h t over Planck's constant, or e to the I times the action over Planck's constant that you get in the Feynman path integral. When you go to imaginary time, it ends up going as e to the minus beta times some slightly different action. And this beta is like, so beta is like, minus beta is like I over Planck's constant. So you're replacing imaginary time by a time that depends on the temperature. And once you have the problem in this form, then all the integrals are convergent and it becomes statistical mechanics. So quantum field theory is all statistical mechanics in disguise as well. And people who do calculations in field theory almost always do them in imaginary time and do this so-called Wick rotation. Okay, so we're not going to do any of that in this class, but that's part of the motivation. So what I'm going to do is I'm going to show you how to do the transfer matrix for the 1D Ising model. We're going to see how phase transitions emerge in this formalism. And then if I have time at the end, which I hope I will, I'll talk about Landau theory and how to do dimensional analysis for field theory. And so next week we will just talk about another renormalization group method, which is a field theoretic renormalization group method. All right. So our goal is to find a new way to formulate interacting stat mech problems, and then in homework 2, connect to RG. So let's start off by writing down the partition function. And so this is just a trace of e to the h sum over I si plus k sum over I si plus 1. So this is the partition function for the one-dimensional Ising model. And so I want you to think of the system being like this. So I have spin 1, then spin 2, so down like that, spin 3, whatever it is, and then spin n, let's say it is up or whatever it is, at the end like that. And then we're going to use periodic boundary conditions. So we're going to say that there's a fictitious spin at Sn plus 1. And this fictitious spin at n+1 is in fact identical to S1. So this is the D equals 1 Ising model with periodic boundary conditions. And nearest neighbor interactions. And the way that you know it's got nearest neighbor interactions is look at the interaction term here. So here it is. And I'm going to just write this out in full. So it's the sum from I equals 1 to n of si plus 1. So if I think of the I as being the labels along here, then when I get to n, then I'm interacting with spin Sn+1, and spin Sn+1 is the same as spin S1. And so that's why in one dimension I can write it in this very nice form. And you use that in the homework. And the reason why it is hard is because Zn is not equal to the partition function for one spin raised to the nth power. Okay, it doesn't factorize. That's the reason why it is hard. And so you can say, well, can we factorize it in some clever way? And so the answer is yes. So the transfer matrix is the nearest we can get to factorizing and interacting many-body statistical mechanical system, or quantum system for that matter. Okay, so I'm going to show you the tricks. This goes back to actually who invented it? Probably Kramers and Wannier in the 1930s. That's where I think it came from. I may be wrong about that. I'm sure I say it correctly. I explain it in my book. Okay, so here's step one. So the step one is we're going to rewrite the partition function Zn. Okay, and we're going to do this in a super sneaky way. So let me write it down for you and then explain what we've done. So I've got the partition function for n spins with coupling constants h and k, and I'm going to write it in this non-obvious form. Okay, so first of all, the trace is just the sum over S1 up to Sn is plus or minus 1, so I don't need to expel that out. And then I'm going to write it like this. E to the h over 2 S1 plus S2 plus K S1 S2. Okay, so that's the thing that's inside here. And then I'm going to do this again. So the next term, I'm going to write it down here, is e to the h over 2 S2 plus S3 plus plus K S2 S3. And then the next term, and then that's going to be, the last one is going to be e to the h over 2. And then it's going to be Sn plus Sn plus 1 plus K Sn plus 1, and that's the last term. But we've got these periodic boundary conditions. And so this term, periodic boundary conditions, Sn plus 1 is the same thing as spin 1. And so this last term becomes e to the h over 2 Sn plus S1 plus k Sn S1. Okay, and then, so this term over here then is now replaced by the term in yellow. So that's the trick. So let's just verify that if you expand this out, then you get the original partition function. So you can see, first of all, that every term, KS1, S2, KS2, S3, all the way up to KSN, S1, all of those terms, all of these are present in the original Hamiltonian. Okay, so all of those terms on the left-hand side here, we've got all of those terms. Now you look at the H's. I've got over on the left-hand side here, e to the h S1 plus S2. So S2 has only appeared times e to the h over 2. Okay, but then you go to the next term, and in the next term, it appears again as e to the h2, e over 2. So therefore, the total coefficient for S2 is indeed just 1 power of h. And so that's correct too. And then what about the starting one? Well, the starting one is e to the hs1. So we have that over there. And then there's no h over 2s1 until you get right to the end over here, and then it comes in there from the periodic boundary conditions. Okay, so what I've just told you is that every term in Zn of h and k is in this reordering of the terms. Okay, so that means that this identity is correct. So that's step one. All right, step two is now we're going to interpret this in a very interesting way. We're going to interpret this as a matrix calculation. So step two, interpret the square brackets. I'm not going to write them out again, but all those terms, we're going to interpret these as matrices. And they're kind of weird matrices. So let me write down what the matrix is, and then we'll see why it is true. So the trick is then to say, I've got a matrix, and it has elements T, S1, and S2, and that is defined to be e to the h over 2 S1 plus S2 plus k S1 S2. Okay, so that's my definition of this quantity T. Now S1 can be plus or minus 1. S2 can be plus or minus 1. And so this, so what I'm thinking then is that the spins are the labels of rows and columns in a matrix. That's the idea. So let's write out what the matrix is precisely. So if we think about this, then what we're saying is that the matrix T, there's a matrix, that's defined to be the following. This entry is called T11. This entry is T1 minus 1. This one is T minus 1, 1. And this one is T minus 1, minus 1. So normally we just say the matrix, the indices are I and J, and their I goes from 1 to N. So T1, 2, T1, 3, T2, 3, and so on. That would be how you would identify the matrix elements. So we're labeling the matrix elements in this way. Okay, there's nothing to stop us doing it, but I could label them. I could label them any way I like. So that is the trick to define this 2 by 2 matrix. And let's write it out then exactly what it is. Because in order to work out what these elements are, all I have to do is put, for the element 1, 1, I put S1 and S2 equal to 1. And so then I get e to the h as my first element. And then my second element, and my second part of that, when S1 and S2 are equal to 1, then I get plus k. So the first element here is e to the h plus k. Okay, so somebody tell me what is the element over here in the right-hand corner, the T1 minus 1 element.
E to the minus k.
Say again?
E to the minus k.
Yes, can you walk us through how you got that? You're correct, yeah.
For the first term in the exponent to the S1 and the S2 cancel.
Yep.
And then the other one is just 1 times -1. Okay.
That's right. Okay, you're Jason, right?
No,
No.
Charles.
You're Charles. Okay, sorry. Okay, don't really get what it doesn't always work. You're Jason. Yeah, okay. Sorry about that. Did everybody hear what Charles said? Yeah, okay. All right, so this is e to the minus k. All right, and then if we go to the next one, it's going to be e to the minus k again. And then the last element is going to be e to the minus h plus k. Okay, because the two minuses cancel out in the interaction term, but in the h term, they just add up. All right, so everybody happy about how to connect, how to write down this matrix. Okay, so that's step one. All right, now let's have a look at what the partition function looks like. So the partition function is Zn of h and k. And so let's have a look at what that is. So that's the sum from S1 all the way up to Sn. Excuse me. And so by definition, so that is T S1, S2, then T S2, S3, then T S3, S4, all the way up to T Sn, and then it would be Sn plus 1, but Sn plus 1 is S1, and so we get back like that. Okay, so that's what we have here on the left-hand panel. That's what it is now in terms of this matrix T. Okay, so now let's have a look at these individual terms. So I'm going to take as an example the S2 term. So let me put that in explicitly over here. S1, S2, S3, up to Sn. Okay, so I want you to look at where S2 appears in this. So we're gonna sum over S2. So there's the sum over S2, and then it occurs here, and then it occurs here, and then that's it. Okay, so let's just take that little sum out of this whole integral, this whole summation. So I've got the sum from S2 T S1 S2 T S2 S3, and this S2 is a dummy variable. And what this thing is basically just the same thing as the rule for matrix multiplication. So let's just remind ourselves about that. So, so if I have two matrices, say A is equal to the matrix B times the matrix C, then in components, then I would have A ij, the ijth element of the matrix A is B I k times C k j, and then I have to sum over k, and usually we use Einstein's summation convention, so we don't write the sum explicitly, but I'm choosing to do so for obvious pedagogical reasons, and so we end up with that. So that's just the rule for matrix multiplication. So then what does that mean for this quantity over here on the left-hand side? So this sum over S2 of T S1, S2, T S2, S3, then this is equal to what? So somebody tell me what they think this is in terms of matrix elements. Somebody who hasn't answered the question yet. Somebody over that part of the classroom. Anybody want to answer the question? One of you guys. So the question is write what matrix is it and which element of that matrix is it? Just from the rule of matrix multiplication. You know?
I'm not exactly sure, but
So you understand why you understand the rule of matrix multiplication I have up here, right?
yeah.
Okay. So in the term that we're looking at, what is the matrix B and what is the matrix C?
So matrix B is TS1, S2.
Right. The matrix B as a matrix, without telling you about its matrix elements, is just the matrix T. And what is the matrix C?
Still is matrix.
It's still T, exactly, right? So when I multiply these two things together, the matrix A is going to be T squared. Okay, so that's good. That's great. Okay, so it's the matrix T times the matrix T, and which matrix element of that matrix is it? Because the left-hand side, we sum over S2, but that means that S1 and S3 are left to be arbitrary. I can set S1 and S3 to be anything I like. So what element of the matrix T squared is it? S1, S3, very good. That's exactly right. So that's what this is. Okay. Anybody have a question about that? You have a question, Andrew?
Yeah, I
Can you speak up so everybody can hear you?
yeah, I mean, I get that, but, you know, in your definition of matrix multiplication, you know, I, K, and J, they denote, positions of entries. You know, S,
They're just telling you the coordinates of the rows and columns.
yeah, I just find it a little interesting that we're letting S1, S2, and S3, which are basically orientations of the spins.
Forget about the physics. Look at the algebra. Okay, the matrix elements are defined instead of having IJ. You know, it goes from 1 to n and A11, A12, A13, and so on, A21, A22, the rows and elements. We're using a different numbering scheme for the matrix. There's nothing to stop us doing it, right? No, okay. All right, so we chose to do it. Anybody else have a question? Yes.
Yeah, but like you mean like S1 sort of stuff, like S2, S3 are some dummy variables, but I don't understand like if it's -1.
So, well, okay, here's how you interpret it. So look on the left side of the screen and look at this equation here where I'm drawing the star. Okay, so instead of defining, I could define I could say I'm going to use the matrix elements T11, T12, T21, T22. Okay, that's how you're used to defining matrix elements, right? Okay, but there's nothing that says I have to do that. If I want to say I is equal to the value of Si plus, I don't know what it would be. Let me just think a second. It's something like this. 1 plus, I don't know, somebody smarter than me can figure it out. I want, yes, S, so minus S J plus 3 or something like that. Okay, there's nothing to stop me doing it. And then, so then those matrix elements become T1, 1, T1 minus 1, T minus 1, 1, T minus 1, minus 1. There's no interpretation. I can call those matrix elements anything I like. So I'm just defining the rows and columns to be related to the values of the spin. Okay, just a clever way to do that. Okay, I don't stand by this. J is minus Sj plus 3. Let me just think. If Sj is minus 1, then I get, I want to divide by, I don't know, 1 or 2 or something. 2, I don't know. There's a mapping that you can do. Can somebody figure it out for me? Well, I did works. Okay, all right. So, are you happy with my answer?
Yeah.
Okay. I mean, you might say, well, why would you do that? And the answer is, well, because you'll see it's really cool. Okay, but that's the trick. Okay, right. So if everybody's on the same page, then now let's go back to our calculation. So now we can see that the pairs of T matrices really just mean T squared S1 S3. So now let's have a look at the whole partition function. So now what I've got is Zn of H and K. So the first two are the matrices T squared times S1 S3. Then that's multiplied by S3 times S4. So that gives me T cubed. So this looks like T, the sum over S1. S2 has now gone. So then we have S3 dot up to Sn. And then I've got T squared of S1, S3. And then I have T, S3, S4. And then all the other T's up to T, Sn, S1. And now I can take these ones together, take the S3 and the S3 and do that sum. And that's going to give me the sum over S1 up to you know, all the next ones. So I get T cubed times S1, S4, and then T, S4, S5, dot, all the way up to T, Sn, S1. Okay, everybody see how that works? All right, okay, and so now, just keep on going. And so then we can say that then is the sum. I get to the end, so I got still got the sum of S1 to do. I go all the way up to the sum of Sn. I do that sum, and so what I'm going to end up with is T to the power n, the matrix T, to the power n. And then I've got the S1 element of that from the first the first one here, and I've got the S1 element from the last one over here. So this is S1, S1. Okay, so it's a matrix T to the n, and it's the trace of that matrix, because when you sum over the diagonal elements of the matrix, you get the trace. So this then is what you mean by the trace of the matrix T to the power n. Okay, so the Z n of H and K is equal to the trace of the matrix T raised to the power n. Okay, so remember we talked about trace as our notation for this sum. You can see now that it is a real trace. It actually is the trace of a thing. The thing it's a trace of is a 2 by 2 matrix multiplied to the nth power. Okay, so let's just write that down. So when we say the trace of the matrix Aij, that is defined to be the sum over I of the matrix A, the diagonal elements of the matrix. So that's what it is. Okay, all right, now, so you might say, okay, well, how did that help us? And the answer is it helps us a lot because we're going to diagonalize the matrix T. And why can we diagonalize the matrix T? Well, if you look at the matrix T, you can see that it is symmetric. So it has this e to the minus k on the off-diagonal elements. So the step 3 is we diagonalize the matrix T because it is symmetric. So how do we do that? Well, I'm not going to go through the elementary linear algebra. Basically, what we do is we take the matrix T, we make a similarity transformation of it by a matrix S like this. And this matrix S is the matrix of eigenvectors of the transfer matrix. And this matrix S has the property that S transpose is equal to S to the minus 1. So what that means is that once I've diagonalized it, which I know I can do, what I will end up with is that the matrix T prime is then just lambda 1, 0, 0, lambda 2, where lambda 1 and lambda 2 are the eigenvalues of the 2 by 2 transfer matrix. And we know that from matrix algebra, that if I have the trace of the matrix T, that is invariant under the similarity transformation. So that is invariant under this. So the trace of the matrix T and the trace of the matrix T prime are the same thing. And so if that's the case, then that means that the trace of the matrix T raised to the power n is also the trace of the matrix T prime raised to the power n, like so. And why do we want to diagonalize? Well, the answer is this. If I gave you a 2 by 2 matrix and I said raise it to the nth power, that's a horrible thing to do. Okay, but if it's diagonal, then it's really easy. So why do we diagonalize? The nth power of a 2 by 2 matrix is something that is awful. but the nth power of a diagonal 2x2 matrix is easy, because all it's going to be is that the trace of t to the n is going to be the trace of t prime to the n, and that's going to be the matrix. That's the trace of this matrix, lambda 1 to the n, 0, 0, lambda 2 to the power n. And what is that trace? Well, the trace is just the sum of the diagonal elements. So now I've just shown you that Zn of h and k is equal to lambda 1 to the n plus lambda 2 to the n, where these are where lambda 1, lambda 2 are eigenvalues of a 2x2 matrix. And you learned how to do that on your mother's knee. So on your mother's knee, you already learned how to compute the statistical mechanics of this interacting n-body problem. Okay, so that's step. I've lost count of how many steps it is. That's step 3, right? Step 3. Okay. So now step 4. So now we're going to say, well, in general, those eigenvalues are not equal. So let's suppose that lambda 1 is greater than lambda 2. Could be the other way around, doesn't really matter. Okay, so then I can write my partition function is then going to be lambda 1 to the power n times 1 plus lambda 2 over lambda 1 raised to the nth power. Okay? All right. Okay, so now let's take the limit, n goes to infinity. So step 5. Now we take the thermodynamic limit. So I can write lambda 2 over lambda 1. So that's just some number. So I can write that as e to the n times the logarithm of lambda 2 over lambda 1. And I can write that as e to the minus n times the logarithm of lambda 1 over lambda 2, and that is a positive number. And so therefore, as I take the limit n goes to infinity, that means that this term becomes much smaller than 1. And so therefore, in the limit as n goes to infinity, Zn of h and k as n goes to infinity becomes lambda 1 to the power n and plus this correction. Times the logarithm. Okay, and so therefore we can neglect the correction term. And so all we have to do now is, in fact, to do the calculation, the bulk free energy of the system per spin, that is defined as the limit as n goes to infinity of the free energy as a function of h, k, and t over n, and then therefore that is going to be minus kbt times the logarithm of lambda 1. So it's even easier than we said. In order to compute the bulk free energy, the free energy per degree of freedom, all I need to do is find the largest eigenvalue of this 2 by 2 matrix. Super easy, right? Okay, so this is the largest eigenvalue. That's all we need to compute. So even easier. All right. So now let's do step 7. No, not step 7, step 6. Step 6 is let's compute the eigenvalues. So what we have to work out is the determinant of e to the h plus k minus lambda, e to the minus k, e to the minus k, e to the minus h plus k minus lambda, and set that determinant equal to 0. So we have to do the hard work of solving a quadratic equation. And so if I work that out, lambda 1 or lambda 2, whichever one you want, looks like this. It goes as e to the k times cosh of k plus or minus the square root of sine squared h plus e to the minus 4k. And then that's the end of it. That's the end of the calculation. So that's lambda 1 and lambda 2, and lambda 1 is the plus sign, lambda 2 is the minus sign, because you want the lambda 1 is the biggest one. And so therefore, that means that Fn, h, k, and t over n, and the thermodynamic limit is equal to minus kbt times the logarithm of e to the k times cosh of k plus the square root. And so that's our answer. And there's no approximation. This is exact. So when I said that we can't factorize, it's true, we can't factorize. It's not Z1 to the n, but there is still a simplification that we can do, and this is the simplification. All right. So that's the exact result for the statistical mechanics of the 1D Ising model. Okay, cover, yeah.
Shouldn't that be H inside the
Which one?
the first term inside the square bracket, shouldn't that be the hyperbolic cosine of H?
This one?
Yeah.
Possibly. It could well be. Yeah, I think it should be. So let me put it as an H. Thank you for noticing. Let me put it as an H, but I'm going to put a warning here. I don't have my book in front of me, so you should do the calculation yourselves and check it. But thank you. All right. Yeah, it for sure is H. Yes, that was a typo. Thank you. Yeah. The other question, Andrew?
Square root of just what you have out there.
What?
In the second, I think this.
There's a square root, which is the thing that's
The first square root. Yeah.
Uh-huh.
Yeah.
Are you asking what is the square root in the second symbol?
Yeah.
In the second line, it's this thing that's above, which is too long to write in. Okay. All right. So that's the free energy. So I have to take the logarithm of that. Remember, okay. So let's go even further. So remember that when we wrote down k, that was defined to be j over kt. So therefore, what I've got is Fn of h, j, T over N is equal to minus J minus KBT times the logarithm of cosh of H plus the square root, in which I'm not going to write out in full detail. Okay, so that's the statistical mechanics. We've solved it exactly. Okay, so one de-Ising model is solved exactly. So that's the end of the calculation. So now I want to give you some comments about this. So question number one, can you get a phase transition? Well, you already know the answer to this because we've done this before in class on ergodicity breaking and so on. But let's have a look. So if you look at this formula here, is there a way that you can get a phase transition in this formula? So that means, is there any non-analyticity?
Square root. If only there was anything, it would be the square root.
Right, but but is the square root analytic?
Yeah, it's not analytic at 0.
Okay, but for t greater than 0, can you get a phase transition?
No.
Right. So the answer is for t greater than 0, the square root is perfectly fine. And so that means that FB is analytic, implies there's no mechanism to get a non-analyticity and therefore a phase transition. That's true if t is greater than 0. Okay. Well, since we know the answer, we're going to go and look at what happens when t is equal to 0. But first of all, let's just say that this is consistent with the fact that the 1D Ising with nearest neighbor interactions has no phase transition or, for that matter, long range order for t greater than 0. Okay, so that's that. So now it behooves us to ask what happens at one dimension, at t equals 0. So let's have a look at this. So then we have lambda 1. So the lambda 1 is e to the k times the cosh of h plus the square root. Okay, go away, try again. Plus the square root of sine squared h plus e to the minus 4k. And so what's going to happen is as t goes to infinity, as t goes to 0, then k is going to infinity. Okay, so what that means is that this e to the minus 4k then basically goes to 0. And then inside what I have the square root of sine squared h. And this is like the square root of x squared. And what is the square root of x squared? Square root of x squared is 1? Modulus of x, exactly. It's the absolute value of x. Okay, it's not x, it's the modulus of x. Okay, so that means that then lambda 1 is equal to e to the k times the cosh of H. And if I hadn't alerted you, you would have said shine of H, but it's not shine of H. It's the absolute value of the shine of H. So we put that on like that. And then what is cosh of X plus the absolute value of shine of X? So you have to work out X being positive, X being negative. And so what that is E to the absolute value of X. Okay, check that. So therefore, what that means is that lambda 1 is equal to E to the K plus the absolute value of H. And therefore, now when I compute the free energy for n spins is minus n kBt times k plus the absolute value of H. And remember that k is J over kBt, and H is equal to the external field over kBt. And so that means then that the free energy is equal to minus N times J plus the absolute value of the external magnetic field. And this then is non-analytic, at H equals 0. And we can see that explicitly, because if I compute the magnetization, which is minus 1 over n df by dh, then let's work out what that is. Well, so the 1 over n cancels, and then j is just j, so when we differentiate with respect to h, we don't get anything. And then we get, when h is, look at the differential of the absolute value of h, we have to take h being positive or h being negative separately. So this is going to be 1 if h is greater than 0, and it's minus 1 when h is less than 0. And so what we've just computed for the 1D Ising model is that when I look at the phase diagram, so let's draw the phase diagram. So I've got my axes. So here is temperature, and here is external magnetic field. And what we've discovered is that only at T equals 0 is there a non-analyticity like that. And as I go across here, across this 0, it's a first order transition because the magnetization is minus 1 for H less than 0 and plus 1 for H greater than 0, and so it is discontinuous. And if it's discontinuous, discontinuity in the first derivative of the free energy implies a first order transition in that direction. Okay, so that's what happens at D equals 1. Okay, so now let's ask what happens in higher dimensions. Well, we can't do the calculation. We're not going to do it in class. But here's what happens. So now we know that what happens is in 2 dimensions, we know now that this transition is now moved out to some finite TC, and across the line H is equal to 0, we know that there is a first order discontinuity. And then we also know that what happens in this direction, there is a second order phase transition, and there can't really be one in one dimension because this critical point is at the is at the origin, so there's nowhere to go on the other side of it, as it were. So this is a kind of sort of expansion of this phase diagram. So this thing here sort of moves over to here like that. It stretches out the discontinuity, and then you get the picture in like this in d equals 2. And if you in fact say, well, okay, here's another question. Why don't we say what happens? Let's suppose we say that d is equal to 1 plus epsilon. So we can say, let's suppose I can think of dimension as a continuous parameter, and then d is 1 plus epsilon. Then you would expect, and it's true, that the critical temperature, then the phase diagram is that Tc is a number of order epsilon. In other words, as you think of it, dimension as a continuous variable, then you can work out what happens then. And so that is a trick that people use in statistical mechanics to do that. Okay, so that's what happens. So this all makes sense. It all agrees with everything we already know about the 1D Ising model. Yes, question.
So for the free energy, the H is in the absolute value bracket.
Yeah.
Would that change your how the magnetization will be computed?
So to compute the magnetization, so remember, so if I've got to differentiate this thing on the left-hand side, so I can write that formula as J plus H when H is greater than 0, and J minus H when H is less than 0.
Yeah.
And then I just differentiate it with respect to H, and I get plus 1 or minus 1, depending on whether H is greater than 0 or less than 0. Does it make sense? Did I answer your question?
Yeah.
Okay. All right. So then you might say, okay, fine. But suppose that you could get phase transitions. I suppose you could get a phase transition in the transfer matrix method. How would it show up? Or another way of saying it is, what are mechanisms by which you could get a phase transition? So the answer to that is going to be a thing called the Perron-Frobenius theorem. So let me explain that. So if you look at our formula, you can see that what we have is everything depends on the largest eigenvalue of the transfer matrix. So because it depends on the largest eigenvalue of the transfer matrix, the only way you could get a phase transition is lambda 1, lambda 1 could be a non-analytic function. Of its variables, h and k. That's in fact what happened at t equals 0. We saw that just now. Then you could have something like this. You could say, well, if lambda 1 equals lambda 2, that could happen. Then that would mean that the square root would equal 0. And so then you might be able to get a non-analyticity that way. And another way is you could have lambda 1 was equal to 0. In other words, it itself could go through 0. And in fact, for t greater than 0 and d equals 1, none of these things can happen. And they can't happen on general grounds. So let me now tell you what are those general grounds. So the Perron-Frobenius theorem I'm not going to prove, says the following. take an n by n matrix where n is less than infinity. Let's call that matrix A. And let's assume that the matrix elements of Aij are greater than 0. Then then you can prove that the eigenvalue of largest magnitude, so lambda 1 in our language, it has the following properties. It is real and it is positive. So you can prove that. You can prove that it's non-degenerate. And C, you can prove that it is analytic in Aij. So our eigenvalue, our transfer matrix satisfied all these conditions. And so that's why then from the Perron-Frobenius theorem, that means there can be no phase transition for t greater than 0. So even before we did the calculation, on general grounds, using theorems from linear algebra, we could already see that there's no phase transition for finite temperature. Okay, so I didn't prove the theorem, but it's a true theorem, and we can see that everything that we thought could make the phase transition, we saw explicitly in our calculation for lambda 1 that we couldn't get the phase transition for t greater than 0. And so you can see that this picture is then telling you the right answer. All right, so then you might say, well, that's very strange. Okay, it's very strange because you can say, well, how on earth do you ever get a phase transition? How do you get a phase transition at Tc greater than 0 in, for example, the d equals 2 Ising model? Didn't we just prove that it's impossible to get a phase transition? Looks like it, right? And by the way, historical fun fact, the model is called the Ising model. Lenz gave Ising, his student, the problem to work out the one-dimensional Ising model and see if there's a phase transition in it. So they wrote down the model, and they did the calculation that we've just done, and they found that there's no phase transition at t greater than 0. So then they said, okay, too bad, this model is a rubbish model. It doesn't describe the cooperative behavior in magnets, because they guessed, well, if it doesn't work in one dimension, it probably doesn't work in any dimension, and so our model is rubbish, okay? Today, we know that the Ising model probably has like 1 million citations, and their conclusion about what happens in higher dimension turned out to be, as they say in Russian, not quite correct. Okay. All right. So how do you get a phase transition in 2 dimensions then? If we just prove that it can't happen. Can anybody see how we resolve this paradox? Think about it, and I'll tell you the answer.
We didn't do it for the 2D, right? We're just looking at 1D. So
We just did it in 1D. That's right. The only calculation I did was 1D. The 2D calculation is much harder. And I'll give you a homework exercise to look at a two-dimensional transfer matrix, not in one dimension, but in a strip. And actually, I don't know if did I give it as an optional question in homework 3?
Yeah.
I did. And I said, you can solve this, diagonalize this thing exactly. Okay. So if you want it, you should try that. Okay. Okay. So, but yes, I didn't do it for 2D, but just extrapolating from what I told you. I mean, how are we going to get around this no-go theorem that came from the Perron-Frobenius theorem? I mean, we have a theorem. We have a theorem, right? Like, I mean, this is mathematics. I mean, mathematicians aren't physicists. You know, they actually know what they're talking about. Okay, so anybody, Gregory?
Yeah, so I don't know, maybe this is not quite right, but what if by introducing another dimension, we have another like infinite amount of terms? So just like we figured out that the partition function is always analytic, but it's not analytic when we have an infinite amount of terms. Maybe something like this happens here too.
Well, it's certainly true that we have to take the thermodynamic limit and it goes to infinity, and we did that in our calculation. Okay. So in all of these things, so the physicists call these things no-go theorems. They're theorems that tell you something is impossible. And usually when somebody tells you that something is impossible, there's usually a mistake in that statement. Okay. And it usually goes wrong on line 1. Okay. So
it's a boundary condition.
the boundary conditions are fine. You can do those boundary conditions in 2D as well. You solve things on the torus.
Yes, but so going back to the thermodynamic, the theorem is for finite.
Mm-hmm.
So
Copy that.
Mm-hmm. Well, but remember that the matrix is n by n. I could call it m by n. Okay, just to make sure that you're not confused. Okay. Okay. So let me change this nomenclature. Okay. So m by m matrix, m less than infinity.
So the n over here is not the same as m. Is that what?
No, I mean when we did the matrix when we did the transfer matrix, our matrix was 2 by 2 matrix. We still took the n goes to infinity limit. Okay, but you're kind of unknowingly for the wrong reasons on the right track. Okay, okay. The answer is this: if I construct the matrix, the transfer matrix in dimension greater than or equal to 2, it is in fact an infinite by infinity matrix. In the thermodynamic limit. So what that means is that the Perron-Frobenius theorem doesn't apply. That's how you get out of it. Okay, so that's that. Now I want to talk. I want to now move on to a new topic. So the next thing I want to talk about is what's in chapter 7 of my book, and that is Landau theory and dimensional analysis. Okay, so what I want to do is my goal in this section is to explain in a different way than we have before. Why phase transitions are hard. Even though there is a small parameter. So let's see what that small parameter is. So the small parameter is the obvious one. I have little t, that's t minus tc over tc. And we're looking at this as we go, as we get close to tc. And so we have a small parameter. So if we have a small parameter, how can this be a hard problem? And the answer is going to be, that's the question. Why hard? And the answer is going to be that we don't have a usable small parameter. And this is something that is, I would say, not as widely appreciated as it should be. So here's what I'm going to do. I'm going to write down Landau theory as the way we've described it before. I'm going to rescale it. I'm going to use dimensional analysis to rescale it in certain ways, and then we're going to see what happens. So the strategy that we're going to do, rewrite Landau theory in dimensionless variables. And see what happens. So here's, I'm going to start off by writing Landau theory like this. So I'm going to define my Landau theory in a kind of canonical way, that we will use later on. So let me write it down, and then I'll tell you what the variables mean. So I'm going to write it like this: integral d dr, and then a half rad s squared plus 1/2 r naught s squared plus 1/4 u naught s to the 4th minus h naught times s. So that's how I'm going to write down my Landau theory, and that's the thing that I'm always calling my effective Hamiltonian as a function of my spin variables s. Now, let's just remind you that the spin variable should have a coarse graining scale associated with it. So I'll put that in like this, and that we are going to write as beta times gamma, so 1/2 times the magnetization. I'm going to call R naught, so this is defined. R naught is defined to be A times T, where T is T minus TC, and U naught over 4 is defined to be 1/2 B over beta gamma squared, like that. So why have I written it like this? The reason I've written it like this is the following. I wanted to make the coefficient of the gradient term to be just a constant, 1/2. Remember that when we derived this originally, quite a few lectures ago, we wrote it down phenomenologically. We also derived it in mean field theory from the Ising model. We saw that the coefficient of the gradient term had a number in it which depended on the interaction strength, which was and the range of interactions. And so what we've done here is I've rescaled, so everything now it has just got the coefficient of grad s squared is just 1. So we're using those units, and then And then written in this way, then the partition function is then just the trace of my spatially varying spin order parameters e to the minus the effective Hamiltonian, and I've scaled beta into this, and so I have it like that. And this is the integral over Fourier components with naught is less than k is less than the cutoff, the coarse graining scale lambda, and this lambda here before was 2 pi over lambda because it was in real space. So this would be the real space lambda, but in k space it would be just 2 pi over that. So I've defined the coarse graining scale in this way. It doesn't really matter how I do it. And what we're going to do next time is we're going to do dimensional analysis. On this field theory. Okay, so that's where I'm going to stop since it's time. I will be happy to take questions outside. So let me turn off the recording. Hi, Reno. Did you have any questions?
No, thank